All right, so we looked at a linear elastic material. That's nice. That's not a very good model for soil. So now what we're going to do is look at real stress strain models for soil. And here's where I'm going to explain to you that E-log P curve, stuff we've done for years and years, probably isn't a very good way to look at stress and strain for soil. So when you get done with this one, this is basically if I summarized all these learning outcomes there, you need to be able to describe real stress and strain soils for real soils, but you need to be able to in two spaces. You need to be able to describe stress strain curves for soils in I want to call them engineering mechanics space, which is linear stress and linear strain, and in geotechnical way we do it, which is the E-log P curve or the semi-logarithmic way we do it, where we take the log of stress versus strain or void ratio. And that also means you need to understand the difference between void ratio and strain. And we're going to go over all that stuff. So let's start with void ratio versus strain, because we do this all the time. This is another thing we do in soils which is really weird and have confused many people in the world. So here's the simplest way to understand the relationship between void ratio and strain. We're going to use our three-phase diagram. So here's a soil. That's air, water, and solids. And if we compress it somehow, I'm sorry, before I start, I'm going to define the volume of solids to be equal to 1 because it's easy. It could be anything, right? But I'm just going to say it's 1 unit. And then the volume of the voids is equal to the void ratio, right? If the volume of the solids is equal to 1, the volume of the voids, because the void ratio is the ratio of the volume of the voids to the volume of solids. And that's the initial void ratio, that's E naught. So I'm just going to define it that way because it's easy. Now, if there's some kind of loading, there's going to be a change in volume. All that change in volume is going to occur in the voids. In this case, I'm assuming that it's undrained, but there's air there, so all the change in volume is just in the air. But it could be that there's water there that flows out. But in any case, all the change in volume is going to be a change in voids, right? Solid material is not going to change. So the change in volume is equal to the change in voids. So what's the strain? What's the definition of strain? Linear strain, normal strain? Delta L over L, right? So what's in this case, it's delta L over L. Well, what's L0 for this little model? If we're talking about vertical compression. 1 plus E0, right? And what's delta L? Delta E, right? So that is the normal strain. It's the delta E divided by 1 plus E0. So that's the relationship. Excuse me. That's the relationship between stress and void ratio change. You need to know this because at least we used to a lot use void ratio, and you'll see people doing it both ways. You got to understand the difference between void ratio change. Now we're talking about volumetric strain. That would actually be a volumetric. If I actually wrote this, I guess most correctly, this would be a volumetric strain, because it's a total volume, right? Okay. Well, we're going to talk about one-dimensional compression now, because this is a very common boundary condition that we have in geotechnical engineering. And so the model of this is, if we're looking at the settlement for a large embankment, and by a large embankment, I mean a case where we're loading some area in the length that has a length W, and you can think of this in 2 dimensions you want, where that length is much greater than the thickness of this compressible layer. So this is like, you're doing an embankment fill for a housing area where it's thousands of, it's going to be thousands of feet wide in each direction, and the compressible layers are 10 or 20 feet or something like that. So in this case, we're going to have one-dimensional compression, which means that there's going to be no strain. This strain in this direction is going to be equal to 0, and whatever's going on here is going on there, is the same thing as going on there, is going on every place. So it's one-dimensional compression. It's not one-dimensional stress, but one-dimensional compression. All the strain is in the vertical direction. Okay? So if we have, and that's the same model we have when we do a odometer test, right? We take a hockey puck of soil, we put it in there, we confine it in these rings on the side so it can't strain laterally, and we compress it, and it's one-dimensional compression. That's the boundary condition. If we have that boundary condition, then the settlement of this is that, that settles down some amount. All we have to do is integrate from 0 to L0 of the vertical strain times dz. the relationship between stress and strain there is that the strain is equal to the change in vertical effective stress divided by M, where M is now the constrained modulus. This is analogous to Young's modulus, except what were the boundary conditions for Young's modulus in the horizontal direction? It was zero. What was in zero horizontal stress? This one is zero horizontal strain. Okay, so it's a different boundary condition, different modulus, and there is, guess what? Is there a relationship between constrained modulus M? I think that's the definition. M is the constrained modulus. Is there a relationship between that and Young's modulus? There'd better be, because you only need two elastic components. That's just there's another one, so the relationship is right there, and that comes right off that table. That the constrained modulus is equal to the Young modulus times the quantity 1 minus nu over the quantity 1 minus nu times the quantity 1 minus 2, 1 plus nu, sorry, times 1 minus nu. And that's in that table that I gave you already. And if the soil is homogeneous and linear elastic, M is constant. If it's not homogeneous and it's not linear elastic, then it's not going to be constant. Okay? So we now know the relationship between the void ratio and strain, and we know if we're talking about one-dimensional compression, the modulus that we're concerned about is the constrained modulus. Well, that's all nice. Oh, and then if it's constant, then I can just do this little linear calculation here that rather than integrating, right? This integral becomes a really simple algebraic equation because m's constant. So the settlement is then just equal to the applied stress divided by the constrained modulus times the original length. Okay. Now, this is the way we taught you as undergraduates almost every place in the world, how we plot the relationship between stress and strain for soils, right? We plot the this is the log, because of the scale here, this is the log of sigma prime of the effective stress as a function of the void ratio, right? And we all know this, and we can draw a straight line through this and the slope of that line, and we can draw a straight line through the reload part at the top. The place where those two connect is the pre-consolidation stress. And we call the slope of this one C sub C, the compression index, and we call the slope of the other one C sub R, the recompression index, right? Everybody knows that. That's the way it's in Terzaghi and Peck. That's the way it's in Caduto, Kitch, and Young. Caduto, Young, and Kitch, right? Clearly the right way to do it. It's the way that Holtz-Kovacs presented. And actually, if you look carefully both in Holtz and Kovacs and in Caduto, Young, and Kitch, you'll find out that they present it both as, this is not the only way it's presented though, but that's the predominant way we discuss it, but it's not the only way it's presented to those. All right. Well, let's take and by the way, the blue lines there are data from a real soil. It's a marine silty clay. And so these are all real numbers. It's not made up stuff. Well, let's go back to engine mechanics and plot that the way everybody else plots stress and strain. Let's plot it as stress versus strain. That's the same curve. And you see that, what is that, a strain, is that a linear elastic curve, a strain hardening curve, or a strain softening curve? That's strain hardening, right? And the red dots, by the way, see these little red dots here? The red dots are also the same as the red dots here. So I think the other one's right there. Oh, no, it's at the bottom. There it is. There's the other one down there. Okay. Just so you know, so that they're at the three unloading points, the first, second, and third unloading point. Okay, well, I plot it this way. What's this slope? The slope of this one is the modulus. In this case, it's the constrained modulus because it's a one-dimensional compression, right? It's not Young's modulus, it's the constrained modulus. And it's not constant. But and this is the equation for that. We already went over that. And if I want to calculate the strain, then I've got to integrate from sigma 0 to sigma f of 1 over m times d sigma. And one of the things I've never understood is why we plot stress-strain curves when really the independent variable is almost always stress and the dependent variable is strain, but I don't know, that's the way we originally started doing it. So these structural guys, the engineering mechanics guys are just as weird as we are. They're just weird in a different way. Right? Everybody with me? That's 1 over m. Now, what we don't like to plot it in geotechnical engineering, we don't really like to plot stress versus strain. We like to plot strain versus stress, which is just all we're doing is flipping the axes, right? And we do that because soils are really compressible. I mean, this is my excuse anyway. Soils are really compressible, so that we like to talk about compressibility instead of stiffness, because we have things that have high compressibility, low stiffness. But they're just the inverse of each other. So the slope of this line is what we call m sub v, which is the volume compressibility. And that's just 1 over the constrained modulus. Nothing. All we're doing is flipping the stress strain curve. Okay? And if I want to calculate the strain now, I just integrate from sigma prime 0 to sigma prime final. Now it's just m sub v times d sigma. Okay? I've just flipped the axes. The volume compressibility is just 1 over the constrained modulus. All right. Let's talk about, now notice these were all in strain space, right? Well, let's talk about void ratio. Because we do this a lot too. We plot stuff versus void ratio, right? Which I don't understand. I mean, I learned it this way. When anybody done how many people have done a consolidation test in the lab? Right? Did you measure void ratio while you were doing that? What does the little dial gauge in the top measure? Well, it doesn't measure strain, it measures displacement, and you started off with a sample that was probably 3/4 of an inch thick or half an inch, right? So we measure, so think about this. So we measure that, you divide by if it's 1 inch thick, you divide by 1, if it's 3/4, right? And so you're not measuring strain, but you're directly, you can easily compute strain. And then you go and convert that to void ratio and plot it versus void ratio. And then in the end, when you're actually doing a calculation, what do you want to know? The change in void ratio, or do you want to know the strain? You want to know the strain. So why we do this, I've never figured it out. And actually on the West Coast, people pretty much never plot something versus void ratio. On the East Coast, they still do that. And in my old advisor at Illinois, God bless his soul, Dr. Messery, boy, he'd turn over in his grave if he heard me talking about something other than void ratio. But it's done, so we need to understand what it is. So we're going to define this slope of void ratio versus stress. This is linear now, as a sub v. It's called the coefficient of compressibility. You'll see this in particularly older papers. And it's going to be, the relationship to m sub v is, remember the relationship between void ratio and stress was 1 over E naught. So it's going to be negative because as the void ratio decreases, the strain goes up, right? So it's negative. Just mv divided by 1 plus E0. And if you wanted to calculate the change in void ratio now, not the stress, but the change in void ratio, just AV times d sigma integrated from sigma 0 to sigma final. I don't think I really understood. I mean, I had to do all this stuff as an undergraduate. I don't think I really understood MV and AV until I actually started looking at linear stress strain curves, and I finally understood it. Because they're telling us what MV and AV is, but the only way we ever saw a stress strain curve was like this, and they gave us the equations for AV and MV, and I never understood it. So now you have a half a chance to understand something that I didn't understand for 30 years. Okay. Now, if we go back to our traditional E log P curve, we said this before, this is C sub C. I'm only going to look at, the only difference between C sub C here and C sub R is where you are in the curve. So we'll just talk about the slope. I'm going to call it C sub C. The only difference about C sub C and C sub R is where you are in the curve. So let's just deal with C sub C right now. Well, C sub C is delta E over delta log sigma. It's not delta E over delta sigma, it's delta E over delta log sigma, right? So that's the same as if I want to calculate this. If I want to calculate the change in void ratio. I don't know why that C is C shouldn't be there. But delta E is C sub C times the delta log sigma is log sigma. Sigma 0. It's log of sigma final minus log of sigma 0. Well, that's just log of sigma final over sigma 0. And this looks like it's upside down. You think, well, no, it's going to be, but it's not upside down because the void ratio goes the other direction, right? Now, what about the way we actually do this in the lab and everything? Or we're plotting strain versus the log of effective stress. What's the slope of the curve now? Well, what was the relationship between delta E and delta E and strain? It was delta E divided by 1 over E naught. So this slope is actually C sub C divided by 1 over E naught. And as far as I know, there's not a common term for that. I have seen people give it a name, which I don't remember what it was, but as far as I know, there's not a common term for that, so I don't think there's a name for that. But now if we want to calculate the strain, you know, it's C sub C divided by 1 plus E naught times the change in times the log of the change. And that's the settlement, right? That's the old settlement calculation we always do. It's always the 1 plus E naught in the beginning. Why? You're probably all like, what was that? Maybe you never wondered why that was there. Well, that's why that's there, because we're trying to convert void ratio to strain. That's why that 1 plus E naught is there. Okay? That's all the same data. It's all the same material, right? So why would we do it one way versus I tell my undergraduate students, why do we plot this thing and make it a bilinear curve? And I say, why would we do that? And they come up with all these reasons. And I said, no, it's really simple. Because we can draw two lines on the semi-log plot. We can draw two lines for a lot of soils, and it looks about right. There's no theoretical reason for it. The soil, you know what? As far as I know, soil doesn't know anything about semi-log space. So let's look at what this really looks like. Okay, so now I've taken a bunch of data from Holsa-Kovacs and some of that you have, and then some other data that you don't. Well, I don't think I've taken any data that you don't have or aren't going to get. Actually, all the data that I just showed you for that marine silt, that's actually the soil in your project. So these are all stress strain curves from real data, from real soils and real places. So this is San Francisco Bay mud. This is figure 8.5 from Holsa-Kovacs and Sheehan. And does that look like a curve that you can make easily bilinear? Well, yeah, fairly. This is not. This is definitely concave down, and something funny is happening between here. But you could make that bilinear, right? Here's the same data plotted in linear space. So even Holsa-Kovacs and Sheehan have done this. And what does that material look like? Here's one thing I want to point out. If we were going to talk about this in traditional terms, we would call this sigma prime C, right? The pre-consolidation stress. And then what you probably heard was, well, that's the point where we pass the greatest stress the soil has ever seen, and suddenly it gets softer after that point because that's what was consolidated and unloaded, whether it was in the lab or in the field, right? And we've crossed that point, and suddenly the soil gets softer, a whole bunch more strain. Well, and that occurs at where? So that's someplace. Let's do a better job. Let's pick that point right there. So this is 10, 20, it's 20, 30, 40, 50, 60, 70, somewhere around 70 or 80, right? Where's 70 or 80 here? Well, this is 250. So 70 or 80 is, someplace right in here. Is the soil getting all of a sudden a lot softer in that area? I don't think so. I can't draw straight lines with this thing, but here's the slope for those 2 points, right? Here's the kind of the tangent modulus right after. Yeah, it's getting a little softer. Is it getting a lot softer? It's definitely getting softer, but it's not like there's some dramatic change. It's not like, it's falling off the cliff here, right? But it's not falling off the cliff there. Yeah, it's getting a little softer. And then down here where this portion is linear, it's definitely getting stiffer, which we knew, right? But I'm not sure this has all that. It's not like there's a gradual change in behavior in this area, and we don't have a lot of other data points that would be helpful me. But in the semi-log plot, it's falling off the cliff, and in the arithmetic space, it's getting a little softer. This is one I really like a lot. So this is out of Pender. I asked you to read this. This is a really easy one to read. This is basically these data. So I befriended this New Zealand emeritus professor when I was at a conference in Europe some years ago. He's a really neat guy, Laurie Wesley, and I've asked you to read one of his papers, which I think was really. He presented this paper in Ireland when I was there, and it was kind of interesting. And then I started thinking more about it and reading more about it. I think, wow, this is really interesting. And see, this is he and some of his colleagues from Auckland. So this is one of the things he's really big about is having people understand residual soils whose behavior is really different than most soils that are transported and deposited, which we deal with mostly in this country. Well, there's plenty of places with residual soil in this country too, but this is a bunch of stress strain curves for residual soils in Auckland. So if I look at these first thing I would say, well, man, those are kind of disturbed samples. Look how there's no distinct, there's no distinct change. But if we were going to pick where the pre-consolidation stress is for all these samples, or we'd pick something. We could do our little Casa Grande construction here. We find the point of maximum curvature. We draw a line there. We're going to bisect it. We could do all that stuff. But we're going to end up with a stress strain curve where this is sigma prime C someplace in there, right? Okay, you ready? This is the same soils plotted in linear space. Now tell me what you see now. They're linear. They're linear. I mean, if you had to model those are linear elastic. Yeah, there's a little. Some of them have a little softening right here at the beginning. But if I was just an engineer, I needed to draw lines through those data. This is pretty frickin' straight. There's no pre-consolidation stress. There's no softening anyplace. There certainly isn't any softening. This thing happens out here at about. This is 500, right? Did I get that right? This is 10 to 2, that's 102, and there's 500. So here's 500. You see any dramatic change in the behavior there at 500, and these soils are suddenly getting way softer because you pass the pre-consolidation stress and suddenly they're normally consolidated? I don't think so. All right, so this is a really interesting test. The first thing I would point out to you is these stresses. What do you think of those stresses? The scale goes up to 10,000 MPa. This is not kPa, this is MPa. And the data go up to 1,000 MPa. So what's that? Is that big, small? That's freaking huge. 1,000 megapascals. How many feet of soil is that? So 18 kilonewtons per cubic meter. Let's just pick 20, right? So first of all, 20 kilonewtons per cubic meter, that's kind of a heavy soil, right? So that's kilonewtons per cubic meter. So a meter of that is 1 kPa, right? So how many meters is it to get to 1,000 MPa? So that's a 1,000. Right. So one K. So it's I'm sorry. It's 2 kPa per meter, right? Didn't do that right. 2 kPa per meter. I mean that's a high number, but that's okay. 2 kPa per meter. So that's point. Yeah. So that's 0.0002 MPa per meter, right? So to get up to 1,000 of those, that's 1,000 meters. Did I do that right? It's pretty deep in the soil. It's pretty deep in the earth. These data were taken for the Air Force many years ago when they were looking at behavior soils in blast. I did meet this guy once. I was actually in a business where we were doing that. So these are really high stresses, is all I'm trying to tell you. So these are really, really high stresses. Okay, but clearly here, and this is for a loose sand, a medium sand, and a dense sand, and there's different behavior, but clearly we've got sigma prime C here, the transition between over-consolidated, normally consolidated behavior. It's occurring someplace around 8 MPa, 6 to 9 MPa or something, right? Clearly, right? Well, here's the stress strain curves for those in linear space. And what do you see? Here's where that big transition is from normally consolidated to over-consolidated, normally consolidated, and what do you see? This is just strain hardening all the way. All this is doing is just getting stiffer and stiffer and stiffer. Well, why do we see this? Why do we see this big change here then? We see that big change because we're taking the log of something and it shrinks things up. Well, the point is we don't think in, we think in linear space. To us things are linear. We don't think in semi-log space. Especially you guys. You guys don't use. You never even know what a slide rule is. You've never known anything about logs. those of us that actually used to have to use log tables to multiply back in the dark ages, back when what we used to call a four-banger calculator cost $30, and that was 40 years ago, so, 35 years ago, so that's, $250 now or something. And all that we did was multiply, divide, and add, multiply, subtract, add, and divide, and we thought that was really cool. Anyway, we don't really understand linear space. So here's one. Now here's another one to look at. This one is a little more interesting, and I'm really going to look. This is for Canadian quick clays. Oh, I need to upload it. Have you guys, anybody seen those videos about the Canadian quick clays that the Norwegian, the NGI put out? I'll post a link to them on Blackboard. So these are those clays that you see that where they get a failure and it turns to water. Essentially, it turns like to mud, and you see this river of mud floating down. They have these in Canada, and they have them in northern. We're going to talk about the mineralogy of them in a while. Anyway.
That's similar to that 1970s thing on Sweden.
Yeah, it's exactly that one. Yeah. That's not Leda. Leda's a Canadian. This is Leda clay. It's a Canadian quick clay. That one's I think Vasby. No, maybe it's not Vasby. That's one of the Norwegian or Swedish quick clays, the northern. But these clays, they do have this. It does fall off the end of the earth here, right? And notice this number's, this sigma prime C's, is somewhere around 200. Kind of sloppy there. Sorry, somewhere around 200 kPa. So I just replotted that, and these aren't from a single test. I've been trying to get some data from these. And I haven't successfully gotten any. I got to find some from somebody. But I just replotted his plot so that I could do the conversion. So there's the in semi-log space. Here it is in arithmetic space. And you might say, well, that just looks just like the sand, but it doesn't really. If I blow up the early portion of this, I see this behavior. And here, guess what? At 200 kPa, what's happening? I am getting a significant softening at 200 kPa. A tremendous one. Look at that. And then it starts strain hardening again. So this is a case where, yeah, indeed, this is acting like a sigma prime C, where there is a big change in behavior at that point. But look how much change there is here. That's almost vertical. So what can we conclude with this? We're going to categorize. Here's my conclusions of this, and I think we're not. We'll see how it goes on here. So soils can behave it can be modeled pretty well as. I want to say I'm talking only monotonic loading here. Obviously, when you unload here, it's not elastic, but at least on the loading curve, that's pretty linear elastic. And if all I want to do is calculate settlement, I don't care about the unloading, right? So clearly some residual soils, and I could have plotted the same thing for over-consolidated soils. I didn't do it. If you stay in that over-consolidation range, it's pretty linear. And you can model those as for monotonic loading. I'm talking for a single loading. Obviously, we're always going to get plastic strain. So when we unload, we're not going to recover it all. But a lot of things we're doing in geotechniques, we're only worried about the monotonic loading. You can definitely treat those as linear materials. Some of the materials are strain softening. If you have a lot of structure in your clay, significant structure like these quick clays, you will get strain softening. But it's got to be a highly sensitive soil to do that. A normally consolidated soil does not do that. For sands and for normally consolidated soils, you do get this continuous strain hardening, and you can model them as linear in semi-log space, but that's just for the normally consolidated part. You shouldn't be doing this conversion from if you see a big change, if you see a big slope change in the semi-log plot, you need to go back and plot that stuff in linear space and see what's going on. Sorry. So here's my summary. For a lot of soils, you'll have an elastic region down at the toe, at the very bottom of the stress strain curve where, and this is where this is the level of strains you get, for instance, in seismic surveys or in propagation of earthquake loads, where it really is. Those are very, very small strains and very, very low stresses. Okay, so that's definitely true. After that, there's some kind of rearrangement of the particles going on. Beyond the elastic range, you can have soils that are relatively linear, and that would be certainly over-consolidated soils, and apparently some of these other residual soils that have some characteristics that give them that. They may be strain softening. That generally only, I think we think of everything as strain softening. It reaches that pre-consolidation stress, but really it's only for these highly sensitive clays where there's enough change in modulus that you really see that behavior. And then for normally consolidated clays and for sands and all soils at a high stress, notice that even the quick clay becomes strain hardening after you pass this real softening point, then it starts strain hardening again. So at high and the sand clearly at high stresses. So for all the other soils, for normally consolidated soils and for sands, you can model them as strain hardening materials. And for those ones, this C sub C equals constant probably works okay. The bottom line is this E log P curve can be very misleading. And the first thing you should do is plot all strain curves in linear space. And then, before you decide how you're going to model them. If it turns out it's normally consolidated, or if it's a sandy material and it's strain hardening, and you can fit a nice line to it, and you can use a C sub C, then fine, do it that way. But if it's an over-consolidated soil, or you plot its curve and it looks very linear in the space you're working, just use the constrained modulus. And then when you're in a case where you've got these strain softening materials, then you need to find a way to do that. I think that's the end of this one. So I'm not going to, the next presentation is, so what Yanbu does, I'll tell you where the next presentation is going. What Yanbu does, I'm sorry, I stopped this, I didn't mean to. So I rediscovered Yanbu just a few years ago. The date of that Yanbu paper is 1990 something, but that's the date he finally finalized that presentation. I mean, that's stuff he was doing for decades before then, so it's much, much older than the date of that paper. But what he does is he's developed a really simple mathematical model that covers all these behaviors with very simple and measurable parameters. So then instead of having, we got this model for this and that model for this and another model, he's got a single model that with changing in the parameters gives you all of these behaviors. And that's what the next presentation is. We'll talk about that at the next lesson. Okay? Excellent.